In this video, I'm going to review amorphous materials. This is not intended as a substitute for what we covered in class, but it's just a reminder because we don't have a textbook for this class, and I want you to keep fresh in your mind the topics that we discussed. So we started talking about phase diagrams and all that, and from the discussion of phases, we said that for solid phases, we can have materials that are crystalline or materials that are amorphous. And we discussed amorphous materials last week. Amorphous materials have a short range order, but no long range order. In contrast, crystalline materials have both a short range order and a long range order. Amorphous materials are not random. The definition of random is that every atomic position can be equal probability. And we know that atoms don't pile up right on top of each other. We know that atoms separate themselves according to their bond lengths and according to their bond angles. So we have an ordering, and that ordering can be short range or it can be short and long range in the case of crystals. Talking about amorphous materials as compared to crystalline materials, amorphous materials typically are a network type structure. So polymers are frequently amorphous. They can also be crystalline or partially crystalline, but most often we think of them as amorphous. Glasses we think of as amorphous. We can also have metallic glasses, although they're typically a little bit challenging to form. We have to quench them at extremely high rates to make amorphous metals. When you think of fluids, like water, the structure of water, and water does have a structure to it, you can also think of as a network type structure. But in water, the H2O molecules are attracted to each other by very weak van der Waals bonding, whereas in a solid, for example, a glass, the bonds typically are covalent and ionic in nature. The example I talked about in class was silica. You see that? Silica. I'm gonna get rid of this marker, I think. SiO2. Silicon is 4 electron valent, which means that it wants to make bonds with 4 other neighbors to have a saturated electronic structure, and it does so in to make a little tetrahedra. So at each one of the corners of this, it will bond to oxygen. Each oxygen wants to connect to 2 atoms to saturate its bonds. So each oxygen will then connect to Si. And then each one of those Si's connects to 4 other oxygen, and that's how the network is formed. If this were crystalline, there would be a regular long-range patterning to this, but because it's amorphous, as you go from one silicon to the next, you may have them twist or turn or stretch slightly in order to make a network of connections. But in spite of it being a short-range order, the long-range order would be absent. Now, talking about the short-range order in silica, for one, we know that the angles made between the oxygen in the SiO2 tetrahedra tend to be around 109.5. There can be some bond bending and bond stretching, but this is the angle that it wants to be at, degrees. And similarly, if we look at the angle here between the silicon, oxygen, silicon, that is going to be 155 degrees. The bond length between silicon and oxygen, again, that can stretch and be moved around some, but it typically ranges between 1.5 to 1.7 angstrom. Remember, we talked about angstrom in class. 1 angstrom is 1 times 10 to the minus 10 meters. And it's not a true SI unit, but it's very convenient because when we talk about bonding, we talk about bond lengths typically being between 1 and 2 or 3 angstrom at the very most. So 1 to 2 angstrom is what we think of as a bond length. So you can see we have this amorphous structure. Now, what makes an amorphous material different than a crystalline structure also has to do with phase transitions. So when we talk about phases, we said that each phase has a unique set of physical properties that are close to homogeneous throughout that phase. And as you go from one phase to the next, there's an abrupt change. And we see this when we see, for example, going from liquid to solid water. We see an abrupt change in volume. And we see that here. If we had SiO2, it can form crystalline alpha quartz, or it can form amorphous quartz. And there are many other phases in addition to the amorphous and the alpha. There's also a gamma and a delta. And I think there's around 12 different phases of SiO2 depending on the temperature and the pressure. Those phases of quartz are actually very important for people in geology because the way that we get these phases is through high temperature, high pressure, long lengths of time processes. So deep in the earth is where we see these other phases come about. So if we made a crystalline value, then a crystalline material, then if I were going up here, so this is a temperature on the x-axis and the volume, or the density if you want to think of it that way, on the y, this is melt, or liquid, then there would be an abrupt change going from the melt to the liquid. And that abrupt change is our first order phase transformation. But we don't have that. And what instead we have is we have this melt eventually becoming a solid glass. Now it has a different slope, and it has the solid versus the liquid. They have different optical properties, they have different electrical properties, but the transition isn't sharp. And rather than having a Tm, a melting point, instead what we have is we have a range over which we have softening, and we call the onset of softening, which I'm going to roughly draw that here, Tg. And we call that our glass transition temperature. Something that makes glass transition temperatures interesting, and just glass solids in general interesting, is that the properties of the glass, the density, optical properties, etc., they all depend on the thermal history. So depending on how rapidly or slowly you cool the material, you're going to get a different response. So let's say this was a relatively quick cool. If we were to cool it at a slower rate, what we might have is something that does this instead. Right? So we're still going to have a glass. But that glass's volume is going to be closer to that of the crystalline. And the way to think of this is to think that, okay, if I go down slower, that gives the atoms more time to arrange themselves and to have a structure which is closer to the crystalline. And ultimately, the material really wants to be crystalline. The crystalline structure has an overall lower free energy, but kinetically is not able to arrange itself, and that's because this melt is typically very viscous. You can think of, for example, if you want to compare pouring molten metal, like a molten lead, to a molten glass. Molten lead, it pours a lot like water, whereas a glass, it pours much closer to a honey. If you think of honey is basically these large molecules. It's about a 50-50 mixture of glucose and fructose, and there are some other larger sugars like maltose, which are multi-glucose that are attached to each other. But because they have that large network type structure and some flexibility in how those molecules arrange themselves, they have a high viscosity. And that's why if you want to think about glass, you think about a glass as being what happens when you put honey in your refrigerator or in the freezer, right? It doesn't crystallize, it just becomes a solid version of the honey. And what's happening when we take this glass and we cool it slower, it gives a little more time for these atoms to arrange themselves to approach that of the crystal. And of course, particularly in the case of silica, if you had a huge amount of time, and I say huge as in like days, weeks, you could cool it down slow enough that it's going to form a crystal. Quartz, it really does not want to form a crystal unless you have kind of geological time frames. And that's also what makes it a very useful engineering material. What else can we talk about here? Well, we can also talk about the fact that in this volume versus temperature diagram, if you then take your glass and you heat it up, sometimes you can get a dip. So for example, let's say we took our liquid glass, we cooled it down rapidly, we got the structure. Now if, as we're heating it, we heat it slowly, so I'm going to make the heating in the blue color, we can get something that does this. And as it gets to that softening point, what's going to happen is the glass is going to dip down, and it's going to dip down and start to approach the structure of the crystal. So what's happening is we have these atoms that are frozen in place because they're so cold they can't move past each other. And as we heat it up, they start getting a little more flexibility, and when you get to the point that you're below the melting temperature, but you're above the softening temperature, the atoms are going to start arranging themselves and heading down toward what the crystalline structure looks like. And that's where you get this dip as we are increasing the temperature. Now, it doesn't always have that dip. That's just if you have a glass that was quenched at high temperature, at high speed, and then as you warm it up again, if you warm it up very slowly, you'll get that dip. If you did the reverse, say you cooled it slowly and then you heated it rapidly, you wouldn't see that, right? You have to think about the kinetics of how the atoms are arranged, where they want to go, and the kinetics of what you're allowing them to do in terms of the rate that you change the temperature. So as I said, this quartz, it really does not want to form. It's not easy for it to form a crystal just in ambient conditions. It's a lot easier for it to form a glass, and that's because it's very viscous, and a lot of that has to do with the fact that silicon and oxygen make such a very good network. It's a very strong network, and it's extremely connected, right? Every oxygen connects to a silicon, so it's extremely viscous. If you think about honey being glucose and fructose, well, this is like glucose and fructose, but significantly larger and more complex in how it's connected. So the melting temperature, the melting temperature of quartz glass is around 197.15 Kelvin. That's extremely hot. And we don't want to operate at that temperature. There's reasons that we want to sometimes use pure quartz. The optical properties are fantastic. The thermal resilience is outstanding. It has a very, very small thermal coefficient of expansion. It's a great material for technical ceramics. But because the processing temperature is so high, it's expensive to work with. As I said, I knew people that used to make these large, high-purity tubes for the semiconductor industry, and all the work was done with oxygen torches because you need to go up to those high temperatures. The glass in your window, you don't want to pay the cost of pure silica. So what we have to do is we have to modify the network. And we do that by adding different chemicals. The most common type of glass that's used in things like glasses for food containers, glasses for windows, there are a variety of what's called soda lime glass. And soda lime glass is still largely silica, about 75% SiO2. This is weight percent. Then it also has around 13% Na2O. So sodium, that's our soda. And then it has around 10% CaO, calcium. And that's coming from limestone, CaO2 or CaO3. So limestone is one of the ingredients. And then that gives us about 2% other. And those others can include Al2O3, it can include potassium, it can include, what's that listed here? Boron, E2O3, CKO. These can be thought of as impurities or modifiers, but the primary constituents are these. Now, why are we putting those in? We're putting those in so that they do two things. First is they will terminate the network. So instead of having this, you can imagine this network, if it's perfect, just being this infinitely large network where everything's connected to everything else. Well, what we'll find is where you have, this is a very rudimentary picture. What we can have is we can have sodium coming in, and sodium has one valence electron, and the sodium is electropositive compared to oxygen, so it's going to sit on the where the silicon is. And we can get Na sitting there, or we can get Na here. Perhaps here, we're going to get Ca. So each sodium will sit there, say there, and it terminates the network. And when you take this huge network and you start chopping it up into smaller pieces, it's going to become more water-like, or more honey-like, if you want to think of it as a, still being a network, but a smaller network, which means the viscosity is lower. It's going to pour more like water and less like a super thick, elastically melt. And that means that, first off, it's going to be easier to form crystalline, and it will. But the other thing is that it's going to depress that melting temperature. So the soda lime glass that you see in commercial products, whether they're beverage containers or they are window glass, in that case, the glass transition temperature is around 570 degrees Celsius. So we add 273 to that, it's going to be around 800 Kelvin. Right? So you see a loss of around 1,000 Kelvin for the melting temperature or the softening temperature. So that's important. The calcium, I should point out, that coming in here, the calcium will still allow bridging, but now instead of each silicon connecting to 4 oxygen, the calcium is just going to connect to 2 oxygen. So it modifies the network, reducing the overall connectedness, but it still has some degree of connectedness. And then the boron, B2O3, Al2O3, those also will sit in place of the silicon. So when we put these impurities in part, they're breaking up the network, but the other thing that's important that they do is they add structural complexity. And that's important for making it easier to form a glass. So this SiO2, I said, it very much wants to be a glass. It does not like to form the crystalline phase just in ambient conditions. It wants to, in order to form those, you have to go to high temperature and pressure and long time scales. As we start to cut up that network, the possibility of getting segregation, getting small little crystallites, it increases. And what we want to do is we want to depress the melting temperature while at the same time not necessitating a really high cooling rate. So adding calcium, sodium, boron, aluminum, potassium significantly increases the complexity, and it makes it more difficult. Even though the network is going to have a lower melting temperature, it's going to be still difficult for it to arrange itself into a crystal because it's going to have somewhere between 10, 12 different constituents. We'll also be adding constituents that have physical properties. So, for example, we make glasses that have that are ionically conductive, and for that we put in lithium, and we have a lithium salt as one of the constituents, and the lithium ions would conduct through this. So when people are talking about solid-state batteries, well, we're talking about having lithium on one side and then some type of collector on the other side, perhaps cobalt oxide. And then the middle part is going to be the electrolyte, and the electrolyte is going to be a very thin piece of ionically conductive glass in which we put lithium in that. And lithium is relatively small, and it's going to be able to pass through the holes in this glass. So we can use glasses as electrical conductors. We also use rare earth elements sometimes in glasses in order to change their optical properties. Cerium, for example. We put that in the windows in cars. It blocks the radiation that passes through in the, I think it's the UV. I check on that. It's either UV or IR, but I think it's the UV range that in the olden days is what caused cracks on the surface of your car's dashboard. And then most of you students probably have no idea what I'm talking about, but if you look at cars that are vintage from the 1970s, a lot of times the dash, the plastic, will be all busted up, and it looks like ground during a drought, and that's because of all the radiation damage to the plastic. And we don't have that because we're putting in cerium. We can also put modifiers that change other optical properties. For example, when people have fine crystal, a lot of times it contains lead. And the addition of lead modifies the index of refraction of the glass. And it's still kind of a mystery to me why a person says one piece of glass is prettier than the other. I have a hard time seeing it. But I know that the glasses that people say, oh, this is beautiful glass, will typically have a large lead concentration. And that's because it changes the way that light bends as it goes through the glass, or changes the way that light refracts as it goes through the glass by changing the refractive index. Let's see if there's anything else about it. Okay, so that's a review of amorphous materials, and we will talk about crystalline materials next.